All right, hello again, everybody. As you guys know, I'm not in again today, so I recorded some more lessons. There's going to be 2 videos to watch this time, both going to be Edpuzzles, same as last time. Your notes packet that you were given looks like this. It's, I think, 5 pages. All right, so please follow along. I will be checking this on Monday, so please bring it back with you to class on Monday, and it will be graded, same as last time. All right, so let's get right into it. Just a reminder again, I'm going to be going through these slides very quickly because you have the ability to pause, you have the ability to rewind, watch it at a faster speed, whatever it is. Okay, so don't just miss the notes. Pause it when I ask a question and you want to try to answer it, and take it from there. Okay, so we're going to be talking about groundwater. And the first thing we're going to be talking about is this idea of porosity and permeability, and that's the objective for the first lesson. So the do now question says, in this picture below, choose the beaker that you think would hold the most water and explain why you chose that beaker. So we see a beaker with a ton of these little balls that are 0.1 centimeters in diameter. We see a beaker with a ton of balls that are 0.4, but there's less of them, and a ton of balls, but even less, that are 0.7 centimeters in diameter. Which of these do you think is going to hold the most water, and why? So again, pause the video if you need to, and write down your answer. Okay, so have you ever seen this before? What is it? Some people have this in their backyards. This is a well. This is a pump, really, to pull water out of a well. Oops, hold on, let's fix the slides here. Okay, so when we pull water out of a well, we actually have to dig down deep underneath the surface to access this water in a place that we call an aquifer. All right, and we'll get to that in a second. Every lake, every river in the world that has fresh water has over 100 times more fresh water underground. All right, so all of the lakes, the rivers, everything that's on the surface, underground there's 100 times more. So there is tons and tons and tons of water for us to access, and we need fresh water to drink. So we got to dig underground to access a lot of this. Okay. So you might think that water from the ground is nasty, but most of it is fresh water that you can drink. Over a third of Americans get their drinking water from underground in one way or another. Okay. So the availability of this groundwater and how we can access it depends on this idea, or these ideas, of porosity, permeability, and capillarity. Right? These are 3 ideas we're going to talk about in this first lesson here. So here's the first thing you're going to write down, where it says porosity in your notes. It is the amount of open space in a rock. Okay, so write that in that box on the left there. Now, let's describe the sediments. When there is a lot of open space, we have a high porosity. When there is not so much open space, like in this picture on the right, we have a low porosity. Okay, so not so much open space. There's little rocks in here that are taking up some of the smaller space, and the bigger rocks, there's nothing in here, so there's a lot more open space. Okay, so porosity can vary with a few different factors. One being the amount of cement, and the cement is that things that are holding the sediments together. Remember from back to learning about rocks and minerals that one of the process of forming a sedimentary rock is cementation, right? So it has to cement together. So the more cement between the particles, the less the pore space. So in this picture on the right, there's a lot of cement here, all this extra stuff, so there's not as much space for water to infiltrate, to seep inside it. Same thing, or the opposite with this one over here on the left. There's a lot more pore space, so there's more room for the water to go in. So make sure you have that written down in your notes as well. The second factor that varies porosity is sorting. Remember sorting from when we talked about deposition. So glaciers deposit sediments unsorted, right? So it's big sediments, small sediments, whereas rivers and waves will deposit sediments sorted, right? Big ones in one pile, little ones in another pile. So well-sorted soils have more pore spaces than unsorted soils. So here on the left, it's well sorted. They're all the same size. And notice that because of that, there is more pore spaces here. Versus on the right, these are poorly sorted. There's big rocks, small rocks, little sediments over here. And because of that, it fills in more of the space, causing it to have a less amount of pore space or a lower porosity. All right, so make sure you get that written down as well. And the third thing is called fracturing. Okay, bedrock that has more fractures or cracks has more pores than bedrock without as many cracks. So when the rock gets broken, gets fractured, whether it be from tectonic activity or other things, we are going to see that there are more pore spaces and more area for water to seep inside of it. Okay, so those are the three things that affect the amount of water that can go inside, or the porosity. So, to sum it up, amount of cement, how well sorted it is, and how much fracturing has occurred. Okay. So, to answer our do now question and write this down where there's that blank space underneath fracturing and there's little stars there, porosity is not affected by particle size. And this is one of the more difficult concepts to get in earth science, because we would think you can fit a different amount of water in this container versus this container because they have different sizes to them. But it's not. Okay, it's only affected by the amount of cement, the sorting, and the fracturing, not by the particle size. So if we say that this one here on the left has a porosity of 48%, that means the others do as well. Okay, it doesn't matter the size of the rock, it matters how well it's sorted, the cement, and the fracturing. So if I were to pour water into this container here, I can pour an equal amount of water in here, as in here, as in here, without any issue. Okay, so each container has an equal volume of sediment and an equal pore space. On the bottom of that first page, write that down. There's a spot, it says each container has blank, fill in an equal amount of volume of sediment and equal pore space. Okay, so that is porosity. Let's talk about permeability. So permeability, on the other hand, is the ability of water to flow through the soil or the sediment. Okay, if that's what permeability means, think of the word impermeable. You may have heard of that word before, but I want you to try to write down what you think that word means. So impermeable, I don't have it written in the slides, but I'll just tell you then. It means it cannot flow through. So to be impermeable means to be impenetrable. Right? You can't pass through it. So permeability depends on soil composition, size, and sorting. So write that down as well. So we have a couple different sizes here, big particles, small particles, and then we also have different sorting, well-sorted and unsorted particles. So let's talk about each of these in a little bit of detail. So you guys are going to write all of this down from this slide. It's in the middle of page 2 on your notes. When we have large particles, they are more permeable, and water can flow easily from space to space. Okay, lots of places for the water to flow through here as we go. But when we have small particles, it's less permeable. It's hard for water to find a path through the soil. It's going to move slower, and less of it is going to be able to go through. When we talk about sorting, well-sorted particles are more permeable, plenty of open space that connects to each other. Again, it can flow through easily without issue. But unsorted particles are going to be less permeable because the small particles fill in the spaces and it doesn't leave a lot of room for the water or the other liquids to move. So if we want to have a nice, very permeable soil or area, we're going to want large particles that are sorted. If we don't want it to be permeable, small particles, unsorted. All right, make sure you have all that. Again, feel free to pause it if you need more time to write it down. We're going to move on. So the amount, the availability, and the movement of groundwater depends largely on these two factors, the porosity and the permeability. Okay, that's in your notes as well. So let's talk about how the water moves through the soil now as it is permeating through, seeping into the ground. So as the water permeates the soil, some of the molecules get stuck on the sediments and do not flow through. This is known as retention. Okay, that is retention. Think about it this way. If you pour some water into a cup of rocks and then you pour all the water out, are the rocks just dry now? No, they're still wet. There are still some molecules of water that are being held onto that rock. Right, so you're going to, if we were to do an experiment like this, where we have some sediment here and we pour water through and measure how much comes out of the other side, the amount of water we poured in, if it's 100 milliliters, we're only going to get maybe 87 milliliters of that out, which means our retention amount would be 13 milliliters. All right, so the rocks are going to hold on to some of that water. Okay, so make sure you have that written down on the bottom of page 2. Okay, finally, we have, actually let me get rid of this here. We're not doing a demonstration, obviously, because this is virtual. So, capillarity is our third and final concept for this first lesson here. So it is the ability of water to rise in small openings. It defies gravity in a way. So, you may have experienced this before, and unfortunately we're not in class, or I'm not in class to show you this, but if I were, we could actually take some food coloring and some water and put a paper towel up to it, and you'll see, and you could do this at home on your own, you may have before, the water is going to rise up the paper towel, almost like it's being sucked up a straw. Okay, it's going against gravity. So that is what capillarity is. It's the ability of water to rise in the small openings. Even though a paper towel is a solid thing, there's lots of little pores and holes in it. So the water is able to get kind of sucked up into it and move through it. A real-world example of this would be water being pulled up through a tree. Okay, so the roots absorb the water, and the capillary action pulls it up and allows it to feed and nourish the surrounding areas, the leaves and the branches and stuff. So here's an example of this. It's kind of hard to see, but in these two straws, the red fluid is lifted up, right? It's above the water line. But in the thinner straw, it's higher than in the thicker straw. So these small pore spaces allow the water to actually travel further up. Okay? And this can be shown in this diagram here. So, as I just said, it says the question is asking why is the water rising higher in 2B? Because the smaller the space for the water to move in, the greater the suction really is going to be to pull it up. So while the water is moving up a little bit in tube A here, in tube B it's moving up much more because there's less space. Okay? Almost counterintuitive. Okay, so that was a very quick porosity permeability. Once again, you guys are going to have this video if you want to rewatch it. Let's move on to the next quick lesson here, which is going to be talking about infiltration and runoff. Okay, so now we're on the top of page 4. We are blowing right through these notes, which is great. So we're going to talk for the next, hopefully, just 5 to 10 minutes about infiltration and runoff. So infiltration is the water actually seeping into the soil. This is how groundwater is formed. Okay, the water has to go into the soil, go underground to be part of that aquifer, that underground lake, we could call it. So that's what infiltration is. So write that down. It's the seeping of the water into the soil to become groundwater. Not all of the water gets seeped into the soil. A lot of it just runs across the surface. We call that runoff. And so definition of runoff, which you also write down in your notes, is just the movement of liquid water on the surface of Earth. All right. So, So infiltration and runoff are opposites. Water that does not infiltrate the soil runs off. It's going to move down the slope until it reaches a larger body of water, like a lake or a stream or even an ocean. Okay, water that does not run off is going to have to seep into the ground, and that's infiltration. So the two things are opposite of one another. So let's talk about the factors that affect this. What is going to cause something to infiltrate more and run off less, or vice versa? Now, there's a few factors here that we're going to talk about, but the first one is the gradient. We should be very familiar with gradient by this point in the year. Gradient is our slope. It's how fast or how gentle or how steep the hill or the land is. As your gradient decreases, your infiltration increases. So write that in your notes on the middle of page 4 there. So let me explain that in different words. As your gradient decreases, that means your slope is getting more gentle. So we're looking towards A. When that happens, your infiltration is going to increase, because the water is going to move slower at a lower velocity, and therefore there'll be more time for it to infiltrate and seep into the soil. And then the opposite can be said for the steep gradient. Okay? So this is what it looks like in our graphs. But write down also where it says A has more infiltration, B has more runoff, because remember, they're opposites of one another. So as our gradient decreases, our infiltration increases, and vice versa. As our gradient decreases, our runoff increases. All right? Gradient decreases, infiltration increases. So that's our first factor. Now I want you guys to also draw, as you see these pictures here on the bottom of page 4. There's a place for you to put your stuff, those lines. Okay. The second factor that's going to affect infiltration is the composition of the soil, the size of the soil. So as the particle size increases, so does the rate of infiltration. Large particles, small particles, more infiltration with large particles, more runoff with small particles. Remember, these are opposites. When I say more infiltration, that automatically means less runoff. When I say more runoff, that automatically means less infiltration. And here's what the graphs for this look like. All right, as the particles increase, so does the infiltration. As the particle size decreases, we see more runoff. Okay. Next part of the soil composition is the sorting. As particles go from unsorted to sorted, the rate of the infiltration goes up. So, if it's sorted, all the same size particles together, whether they be big or small, we're going to have more infiltration. If they're unsorted, which is all different sizes together, it's mixed, we're going to have more runoff. Okay, and that's what the graphs look like. As we're better sorted, we get more infiltration. As we're unsorted, we get more runoff. All right, make sure to write all of that down, please. Okay, now we're on the top of page 6, and we see that the rate of precipitation. Remember that precipitation, guys, is the water coming out of the sky, whether it be a solid water like snow or hail, or a liquid water like ice or sleet. This is going to affect our infiltration rate. If there is so much water, we're going to see an increased amount of runoff, which is why we get puddles after storms. So more rain, more runoff. Less rain, more infiltration. Pretty straightforward. Here's our graphs. Rate of precipitation, as the rate of precipitation goes down, infiltration goes up. Rate of precipitation goes up, so does runoff. More rain, more runoff. Less rain, less runoff. All right. Finally, we have the amount of vegetation. So plant life. As you have more plant life, runoff decreases, so infiltration increases. Lots of plants, more infiltration. very few plants, more runoff. The roots and the plants absorb the water, right? So they're going to allow it to infiltrate the soil. It says it right here. Plants take in water. But if there's no plants, a lot of that water is able to run off. Okay, so finally, here's our last two graphs. Amount of vegetation goes up, infiltration goes up. Amount of vegetation goes down, runoff goes up. Okay, awesome. So, we're obviously not going to do an exit ticket. I think that's all I had for that. Great. So, guys, that is going to conclude the first video. I'm going to make another one for the last two little mini lessons, and I'm going to post that as well. So, we're doing pretty good. This was only 21 minutes long. Some of you are going to watch it faster. Others you're going to want to rewatch points. That's totally fine. Yeah, so I'll see you in a couple minutes in the next video.